Okay, hello ladies and gentlemen. Welcome to our first lecture of data analytics, which will cover the introduction to statistical modeling and certain organizational aspects. Lectures are being recorded. We'll see how it will work. There is a bit of echo here. I hope to use a head-on mic, but the one I got generated so much echo that it was unusable. Hopefully my mic from the notebook will be enough. Okay, without further ado, lectures will be done in English. They will be recorded and placed on YouTube. As I mentioned to you during the classes, there probably will be some delays. Generally, you can find me in this building at the second floor in room 214, or you can email me using my email jb@agh.edu.pl. The final grade of this course is 50% the mini projects that you'll be doing and 50% the oral exam. The oral exam, if everything is okay, will happen in person in my room, so in 214. You will be given complete lists of topics that you need to prepare, as in previous oral exam that you had with me. And course materials will be available on GitHub. With, of course, requests to make issues if you find errors or something like that. But this year they will be available in a different way than previously, because previously I just shared the slides, but now I'm writing a book which the topic of this course covers part of it, and this part I will be sharing as I'm writing it online in the form of Jupyter book. So there will be a Jupyter book with, if you've seen some O'Reilly books, for example, how it looks like, it's a clickable book in HTML that you can see with code and stuff like that. And if it will work, it will be made available to you chapter by chapter, depending on the lectures that are happening. So I hope that I will have started today, but had some issues with setting it up to work properly, to generate nice figures. So I need to work a bit on that, but after that we'll be able to make it work. So slides will tell the same story, but in a more visual form, and the book will have some text that you can learn from for the exam. So I think that will be a combination that would be useful for you. So no slides, but lecture notes, okay, prepared by me. But of course, your notes are always recommended, because to remember stuff like that. And of course, I do not guarantee how the text will be appearing frequently. So this is something that you need to take under the consideration. The course outline is like this. We will generally divide it into 5 sections, which probably will be presented in this order as here, because generally these are chapters of the book, so that's the idea. And at first we'll discuss the introduction to statistical modeling and generally Bayesian statistics, which will be our main focus of this course. Then we move to the methods of Bayesian computation, so we'll cover how to compute, what is the way the inference happens, how we go from the mathematical model to the actual inference, useful results. Then we'll cover how to create models in a structured way. So we'll cover models that come from regression, like simple group models, regression models, hierarchical models, methods of how to create models. Then we'll move to the functional data. So generally data represented as time series, and we'll cover different methods of representing that data, either as functional representations, or by time series representation, or by using Gaussian processes. So there will be a way for And we'll focus on one-dimensional case because two-dimensional might be a bit too difficult. And then we'll switch to model evaluation methods. And in the model evaluations, we'll cover the ideas of how to verify if our model is good and how to compare other models with each other. So that's the main idea at the moment working, and we will be covering those in probably this order. Source material. Generally, we are working on 3 books that are our main source material at the moment. Possibly those that I will mention in a moment will also take a factor. So one is the classic book on Bayesian data analysis by Andrew Gellman, which is freely available on the website, and the author there are lectures that cover the material in the way that is presented in this book by Professor Aki Vehtari in Aalto University in Finland, and you can find those lectures in their university Panopto, and they are freely available to use. There are some examples in R, but they are easily transferable to Python, so there are no problems with that. The second book, which is unfortunately not freely available, but is a really good piece of literature that is useful for getting the ideas of Bayesian analysis. It's a book by Richard McElrath titled Statistical Thinking. In this case, the second edition. This book is self-teaching material. This is the material that you can learn directly from going chapter by chapter to learn how the Bayesian statistics works. And it's more code-oriented. The examples are given not in the form of equations, but in the form of R code that you can use to sample or something like that. And this book also has a nice coverage of YouTube lectures, which are available at the website of McElrath. So, but unfortunately, you cannot legally get the book in electronic form. You need to work for look for this in some different way, or order it yourself. And third aspect are the case studies by Michael Betancourt, which are in a way a book in progress. They are freely available, mostly, in the on his website, Beta and Alpha GitHub.io, and the links will be provided, I think, on UPA or in the README of the course for all those links I'm mentioning here. This is very work in progress, but it has very interesting concepts and very well prepared, very in-depth presentation with reservations that some of those this is a combination of statistical nomenclature and physics notation, and this can be difficult to stomach at some moments, but he makes very good illustrations, very good examples. This is most abstract of all those ideas. All those books mentioned before they give an examples from life. His examples are more abstract, general ideas, but on the same time they are more universal, so they can be represented to different cases. I will try to balance both those approaches in my lecture. Some extra reading, so which can be useful to get knowledge by yourself. There is a book by Ben Lambert called A Student's Guide to Bayesian Statistics. This is, let's say, a second modern book with Bayesian statistics. First modern book is the Statistical Rethinking by McElrath, and Lambert's book is the second modern book that represents the general ideas in accessible way, and it's not tied to some older concepts that are still available in literature. This book also has some YouTube examples given to it, some codes using Stan. Unfortunately, the book is in such format that it's difficult to read electronically. So this might be an issue. This is a book good in paper, not only also, there are some books oriented more in Python. So they are focused on using Python environment for Bayesian computation called PyMC or PyMC3 in the older version. Now they're switching to the PyMC name without a number. And there's a book by Osvaldo Martin called Bayesian Analysis with Python, which is generally tutorial for PyMC and RDS packages, and it does not provide you with good theory for Bayesian computation. So if you know what you are doing, it is useful. If you don't know what you are doing, you can get into some problems very quickly. And from the same author with cooperation, there's a newest book called Bayesian Modeling and Computation in Python, which is also freely available on the book's website. This is in the form of Jupyter book. So there are some books, there are some chapters and some notebooks giving code examples. Generally, it's I haven't read it yet. It looks okay. It looks more advanced. It's certainly more advanced than the previous book by Martin. It's more theory, more general ideas, but also some new ideas, some more cutting-edge concepts. So I cannot fully advise it one or another way. It looks interesting. By looking over it, it looks interesting. If someone wants to look into that, that's always a good idea. I cannot fully recommend. However, I strongly advise you not to look into other books about Bayesian statistics, at least at the moment. There are some books that are okay for getting a general idea. A book the book titled Probability Logic of Science by James, which is a more philosophical approach that gives you an idea what Bayesian computation, Bayesian statistics is all about. It is very application removed. This is a very theoretical book. It's not a sense that there's a lot of formulas, but there's a lot of, let's say, discussion of the topics, how it should work. It's a good read, but nothing more than that. There is a book by Sivia called Bayesian Tutorial, Data Analysis Bayesian Tutorial, which is a short book, and it's nice to get you some ideas how Bayesian things work, but on the other hand, it's all those things that are there are not applicable, or they are very problematic when you try to apply them. And because there are some ideas that work for certain given cases, and they show it you as a way of generalizing it, and you cannot generalize it, especially for models with multiple parameters and stuff like that. Other books are very dated. They give you they put a lot of focus on things that are not really do not really matter anymore in practical computation. So I suggest not looking into them. Those books are fine. Going deeper, it's on your own risk to look for some interesting concepts at most. A lot of Bayesian statistics is happening on Twitter. There are lots of people that are sharing a lot of information there. I recommend, of course, Professor Aki Vettari, who is grouping out, works on probabilistic machine learning. So they have a lot of interesting things. They are sharing their work. Professor Andrew Gelman is one of the leading researchers in Bayesian statistics in the world. He wrote this book, Bayesian Data Analysis, and he's responsible for the development of STAN in a way, and at least the main algorithms for STAN that are now being used, so-called no U-turn sampler. Michael Betancourt, I've mentioned him before. He also shares a lot on Twitter. Like his Twitter posts are previews of what happens, like he later develops in his case studies on his website. So there are some interesting things you can get. Richard McElrath also has a Twitter account, shares his lectures, some information, some of his work, that might be nice. And Alex Andorra is one of the developers of PyMC, who has a podcast on Bayesian statistics, which might be interesting to get you the general ideas of what you are doing. However, you should know about what's happening. So these are good people to follow. Generally, Twitter is a nice place to find some interesting scientific stuff if you look properly. A lot of people are sharing their work, sharing the papers they read, and stuff like that. So those are things that might be interesting. Also, there's a good coverage of current geopolitical situation, faster than any news website. So if you properly discriminate, it can be very good, useful information source. Okay, so let's after this introduction, let's move to the general concepts. So what we are doing here, we will be focusing on Bayesian data analysis, and we'll try to explain probably a bit in today, but generally more in the next lecture, what is this. And we'll focus on statistical modeling. So not black box modeling, but statistical modeling will. Our work will focus on models that are grounded in probability. So we will be using models that give you representation of data or processes of phenomena that give you the probability of what's happening, some kind of distribution of results, not one number, but a distribution. The advantage of these approaches is that our results will be interpretable, so we will be able to understand how the results were obtained. And those results will be maximally transparent because our models usually are created in a parametric form and we know which parameter represents what. So even if our model has functional components, those components are related to some kind of parameters which has some interpretation. So we can look into the model and see what's going on, at least up to a certain degree. So generally, what is data science? Data science is a very multidisciplinary field that is getting more and more advanced as times go and encapsulates more and more aspects that's happening. So it's usually something that data analysis is something that we want to use to convince someone to do. It has to have some kind of business justification, what is being done. It has to answer certain problems, and we can, and it encapsulates such things like machine learning, statistics, numerical computation, data engineering, programming, and all of those things that come together to create the actual work. And in practice, data scientists should be able to handle both machine learning and statistical modeling techniques and a lot of other stuff, for example, linear algebra and numerical methods, to be able to handle issues. In many cases, people go to just one benchmark, for example, just tuning the parameters of a deeper neural network to get some kind of gains, but really in order to solve some problems you have to sometimes look outside of the box. And we will now cover why what's the difference between statistical modeling and machine learning in practice. So these things are very similar to each other because at the end of the day we want to get from some information, some data to get some answers. Those answers can be predictions, those can be classifications, or those can be some kind of rankings, stuff like that. So we need to get some kind of answer. However, their difference is how those things are getting one to another, which is the how you get from those data to your answers. And generally, sometimes people try to compare statistical models to the machine learning models, and this is inherently wrong because those are things that are useful for certain aspects. So when you make such comparisons, this comparison will be naturally unfair, either for machine learning or for statistics, depending on what you want to do. If you're solving certain problems that are better suited for statistics, then machine learning will fail, and the opposite. So it is important to be able to distinguish which method group works best for which context. So in statistical models, we focus on, first of all, we focus on probability. So we want to represent certain kinds of uncertainty that happens in the process. So we already know that we do not know everything, that our data is flawed, that our knowledge about the process is flawed. We do not know everything. We have certain uncertainty about what's happening. So in statistical model, we need to consider not only the process, but also the data generation, how we got our data. Is our data complete? Is our data measuring the actual value, or is it measuring something that's only similar to that value? For example, noises or errors, systematic errors, non-systematic errors, losses of information. So we need to, sometimes in order to solve an issue, we need to model the process. We want to look for the interpretability. So we want our model to be able to, when we use our model, we want to interpret the decisions that were made. For example, if we created a maintenance system, and this system decides that this part needs to be replaced. So we stop the machine, and we send the personnel to replace the part, which generates some kind of cost, both stopping and later starting and replacement. And during the replacement, we find out that either the part was damaged or maybe not. If it wasn't damaged, so we need to be able to verify how we got to this decision, why we decided that we need to replace it. Maybe our model is too conservative, or maybe it found something that wasn't there, some kind of artifact. So we need to be able to interpret how we get to decision. And of course, we can get the opposite situation, that we have not decided. We have decided that there is no need for replacement, and failure occurs. If failure occurs, then we need to be able to find out why our model, our maintenance support system, did not suggest replacement. What was missing? So why the decision that everything is okay was made. So this is interpretability. We are able to interpret why something happened. By the way, heat maps on images are not interpretability. Heat maps on images are heat maps on images. That's it. Because there is a lot of work on explainable AI and explainable deep neural networks. This doesn't work. Generally, statistical models are based on some kind of functional relationship between variables, independent and dependent variables, which we often call regression, but this is a very limiting term that generally is not necessarily correct in all cases. The regression has good representation, it's a regression to the mean, but in most cases it doesn't happen. And the statistical models are not limited to linear, but the additive structure, generally the structure of the model has to be given by the modeler. It can be additive structure, it can be multiplicative structure, it can be a power structure, but this structure is a part of model creation. So our model will not, maybe I need to add the charger just for this situation. It stopped recording, it did not, okay. So, generally, those models are structuralized and not necessarily linear, but structure has to be given. In case of machine learning models, we have different situations. First of all, machine learning models are often called non-parametric models, called non-parametric models because they do not have traditional structure or traditional parameters. Usually, for example, neural network, we do not specify individual connections. We specify how many layers there are and how many neurons per layer there are, for example. But we do not go into the detailed connections between every neuron, and we do not focus on each parameter. Those things happen, let's say, more or less automatically. So we do not focus on individual variables, especially that those variables not necessarily make sense in the machine learning context. If we have the function, for example, convolutional neural network, we are transferring the image into some kind of feature space by convolutions. And then we go through that and we get those convolution parameters, which we then feed to layers of neural networks to get some, for example, classification or prediction or detection or something like that. The machine learning models very rarely aspire to create the model of the process. They do not create the model of the process, however, they can learn the relationship between input and output data. So, neural network will not create you a model of the process of why something's happening in it. So, it will not create a qualitative representation of the phenomena, but it can create a very good quantitative representation. So, how the numbers will align, and those predictions can be very, very good. Because it does not rely on additivity or on a kind of structure, this structure is kind of generated by itself. It can be through the neural networks, or it can be some kind of boosting method, or some kind of bugging methods. Sorry, I just need to take it. Hello? Słucham. Halo, słucham. Halo? Nie bardzo. Okay. Okay. Sorry. This is not to introduce themselves. Okay. Either way. Because of this non-parametric, non-structural relationship, this structure can be recreated. And when we are considering machine learning models, we can, its own structure either can be by layers of neural networks, or if you are using trees, decision trees, those trees can be created, or if we are using some kind of bugging method, like for example random forests, then multiple trees are generated on limited subsets, or we can use some kind of boosting method. So we are creating a simple model, then we get output of this model, which are residues of this model, which we then fit into another simple model, and another, and another, and another, and another. This is some, those methods like gradient boosting. So they are just, for example, AdaBoost. The more classical, or XGBoost, the more efficient one. Method of creating the representation, but again, this is a quantitative representation. Numbers, but from relationship between input and output is coded. So, machine learning has a lot of advantages. It's not that statistical modeling is the only way of doing stuff. Machine learning is generally very good situation for high signal to noise ratio. What does it mean? It means that noises that are happening some kind of disturbance of our data are very small in relation to the signal, but not only by its values, but also by its structure. For example, when we have visual data, we have a picture, and the picture is blurry, we can still see the structure in this. If it's a picture of a room, we can see it's a room. If a person is there, we can see it's a person. We do not have the details of that person, but general structure of the image is preserved. So while it's not perfect representation, the structural information is here. So in case of images or sounds, we have very high signal to noise ratio. Those are information when data is just very, let's say, high quality for the model. So the randomness of the data, it does not influence the inference too much. Then machine learning shines, especially that we have a lot of data, because machine learning works the best if you have a lot of data, of good quality. Then you are in a good situation. However, of course, machine learning is a black box approach, which is a good and bad. Bad, no interpretability. Good, you need less prior knowledge about to create the model. You just need to know what kind of data you have, what kind of data representation it is, but how to feed it to your model. But then you don't have to think about all the mechanics that are happening inside. So that might be advantages, or maybe those mechanics are completely unknown, and then black box approach is not a problem because we cannot create an interpretable model anyway. And generally, those situations, machine learning can be very, very efficient, and that's why it's being still used. In case of statistical models, we have advantages in a situation where the machine learning has problems. So it can work on small data sets. As long as we can provide with some kind of other information, we can create a model that, of course, because of small amount of data, will give us uncertainty, but it will quantify our uncertainty. So we will know, in case of machine learning, we get usually a value, yes, no, or number in case of prediction. In case of statistical models, you usually get a number, which is, for example, a mean of a posterior distribution or median or something like that, and you get the uncertainty estimates. So, for example, confidence interval. And in such situation, you know that, okay, I don't know the actual value, but I know that for 95% this value is in this interval. So, in case you have less data, your confidence interval will be wider, but still your model gives you something which you can use and of course propagate this uncertainty through your model to get some inferences. But for example, you can then make a decision that uncertainty is too high to risk. And this is also an answer. If you just get a machine learning model, even if it will work, you get the one number, and this aspect of uncertainty will not be represented by your modeling. Of course, those models are, as I said, transparent, so we can see what's happening on, and we can use them to study the influence of certain predictors of certain variables on the outputs, so we can analyze the relationships more consciously, know what's happening and why. Okay, so generally, machine learning, yes?
Why the white box approach is not a good one for machine learning?
You can't make a white box with machine learning. That's the main problem. White box approach is that you know exactly what is inside the model. And in case of machine learning, well, you theoretically know that you have the what number of layers and what are the connections or what are the weights in the model, but those information are not, like, it doesn't change much in your understanding of the model when you look at inside of neural network, for example. You know that it's a very complicated relationship and you cannot get anything about this relationship. It doesn't have basic, for example, in physics or in some kind of other knowledge. So that's the main problem in machine learning models, that they are black box models because they just do not give you the information of what's inside.
Okay.
So, as I said, machine learning, for the same problem, machine learning, to get good, reliable results, usually will need more data, and those data should be of better quality. Because uncertainty propagation through machine learning models is a difficult aspect. In case of statistical models, we need to specify the interaction between certain predictors and certain and output variables. That's the white box approach, that we specify that this value needs to influence the output in this functional way. And this is, and it won't change the way in our model. It will only represent it by these functional relationships with some kind of parameters, which will focus. So, for example, if you decide that there's a quadratic relationship, you have, it will always be quadratic with reasonable assumptions. It will always be quadratic with parameters, with some kind of parameters. So maybe it will be reduced to 0, or maybe it will be very increased, but still it will be quadratic. In case of machine learning, these associations, these relationships, is being shaped more freely. There's a theorem that a neural network of 2 layers can approximate any kind of one single variable function. So it can fully approximated without any issues. So, for example, so it can handle those things, but again, at other cost. Machine learning can give you better predictions or better classifications, especially in large amount of data, because in case of computation, statistical models have to, except most the simplest ones, have problems with large amounts of data. Especially like going to millions of samples of data. There are issues. That issues come from computation. And machine learning can handle those things better. So if you have good quality representative data with large amounts, go for machine learning models. Because if it's representative, it covers all the cases, you have a lot of the data, so it varies enough, you have the good quality, so no problems, and computationally it will work better, because machine learning relies on solving an optimization problem of some kind. So you need, in case of neural networks, it is least squares usually. So you need to find the weights and the coefficients of neural network in order to minimize certain error function. So it gives you one number, one set of parameters. And that's an easier problem. In case of statistical models, usually you need to, in some kind of way, reconstruct the probability distribution, which can be very high dimensional, very complicated. We will cover that, why it's that complicated. And that's why machine learning might be better for that situation. But in case of you have less data or non-representative data, for example, you have only one result about failure and and a lot of results of proper work, then machine learning won't give you an advantage here. It will make only your life more difficult. Moreover, it will have problems, for example, in situations when the issue did not occur before. How you can teach a machine learning model if the event hasn't happened yet? It was an important aspect when people were searching for dropped nuclear bombs in the Atlantic. Because when planes were flying, sometimes the atomic bomb would just fail and it would just drop into the sea. And how to find it, how to create a model that represents it. And statistical models were useful because you could assign the probability of loss and then kind of. Generally, machine learning has a lot of vocal advocates that say that machine learning solves everything. Even they say that machine learning will create an artificial intelligence which will kill us and singularity and stuff like that. These are not possible things, at least not at the moment. We are not able to find a way to computationally solve problems that are possibly that's solvable for human brain in a way that especially in case of generating new ideas. There was analysis that if we wanted to create a full model that handles the uncertainty aspects that people handle every day, the computational power that's needed is much, much higher than computational power of human brain. So our algorithms would not be able to run on human brain in order to solve the problems that humans solve every day. Because human brain creates some kind of heuristics, some kind of relationships that are unknown to us at the moment in their representation, how they are created, and by those heuristics and associations that are in our brain, which we do not completely know how to work, we function, and we realize very complicated mechanical tasks. Like, for example, moving your hand like this and not falling is a complicated task requiring balancing of very multiple linked body problem that is computationally very difficult. In case of control theory, making such movements with keeping your balance is extremely difficult computational problem. And moving it, humans just do it because of heuristics that were created some kind in our brain associations, which completely do not work as artificial neural networks. So this is it. Either way, machine learning is popular, has advocates, but it is not end of it all. And as I mentioned before, statistical models require you, there are some issues with large data sets. that causes the need to look into the problem deeper, to look either for data reduction or some kind of data representation that will get the information that is in the big data or large data to get something working. So when we can use statistical models when signal to noise ratio is small, so we have noisy data, and those noises can be just measurement noise, or this can be a lot of missing data, or this can be multiple other things that when there is a problem with the data. Where are issues with training data? There is not enough of it. We cannot just do training as usually. We are interested in certain relationships. For example, we want to analyze in experimental way how adding certain substances to results, for example, in biochemistry or virology or just chemistry, when you want to create the relationships. Find, for example, appropriate doses of something. Then you want to evaluate how the one parameter aspect changes everything. And of course, additivity or structure is very important, and we know this structure and we know this relationship. We work with smaller samples. We are interested in interpretability, which is now more and more legally required. For example, European law now requires certain profiling algorithms to be fully interpretable. So you will be able to know how certain algorithmic decisions were being made to, for example, credit score certain people. And of course, when we have advantages of machine learning, as I said, good quality data with no limits, a lot of even unlimited training data, so a lot of images, a lot of sound samples, a lot of text samples, and we are interested in overall prediction value. So in such cases, machine learning models can get you better prediction just by point, giving you one number. If you are not interested in uncertainty, and you have a lot of data, those predictions from machine learning might be better. It not necessarily be a significant difference. It's like single percent of quality. It's not the like 30% to 90%. Uncertainty, otherwise, when we are not interested by uncertainty, we just need the number. And with a lot of data, we know that uncertainty will be low anyway. We are expecting nonlinearity, so complicated relationships that we are not able to identify in other ways. We accept the black box results, and we have, again, huge samples to work with. Okay. And what we are doing here, or we will be doing here, is Bayesian statistics. And Bayesian statistics has generally 3 essential steps. First of all, we want to set up a full probability model. So we want to create a model that will represent the entire knowledge we have about the process. So relationship about what we knew before, what we know about the data generation process, what we know about the relationship between the data and our parameters. So we want to create a model that represents our known relationship between parameters of our model in the structure that we've selected and the data. So in other words, representation of how our data would fit our model if we knew the model parameters. Then we want to create the conditioning on the data. So we provide our data in order to get conditional relationships between parameters and the data. And then we check and evaluate this model, and especially the posterior distribution, so our information that we know after, that joins our a priori knowledge, so what we knew before, with data, so we know what happened, what we knew before the experiment, what experiment added, and the result is the posterior knowledge. So we join our knowledge in the final step. And we are focusing on the Bayesian paradigm because Bayesian paradigm in many ways is significantly more advantageous, especially for engineers or for social scientists or other people from the classical frequentist statistics. Because generally, there are two ways of doing statistics. The classical way, or known as frequentist way, relies on certain formulas, hypothesis testing, especially null hypothesis testing, and different statistics that are being used to test for something, and lots of it is related on the asymptotic approximation. So everything works as long as you have infinite amount of data. Then all those formulas reduce to normal distribution or something like that, and everything works. And that was the advantage of these approaches for many, many years, because this was something that you could actually compute. Bayesian statistics, which we'll cover in a second, in a bit, requires a lot of resources for computation, because Bayesian statistics requires you to solve very advanced mathematical problems, which are actually solvable now thanks to computers and their appropriate use. But there, besides that, so instead of the difference in computational aspects, so one has formulas, the other has problems to solve. The differences are more philosophic, because in case of classical statistics, all the results are based on this. Here is our process. The process has certain parameters, fixed parameters. Those are concrete values that we have of our process. We build it, it has concrete values. And this process can generate data, multiple kinds of data. So very many kinds of data are possible. The idea in classical statistics is so that data is varying, the process is fixed. So all the ideas in case of statistical computation in classical way rely on varying the data to see how it fits models. So for example, bootstrapping algorithms. In case of Bayesian statistics, it's completely opposite. The only thing that is fixed is the data, because the data is something that we've obtained. The data might be an imperfect representation of actual phenomena, because the data generating process was some kind of flawed or randomized, noisy. For example, we know that measurements from the sensor are not the actual values of the voltage, let's say, just the measured value with some kind of noise that happened during the measuring process, right? So for example, like when the analog conversion happens, there are some things can get disturbed. When we use the digital analog digital converter with quantization, right? Our values, for example, we have 12-bit converter, so this converter converts the data only to possible limited number of values. Let's say 4096 values, possible values, right? So this is something that that is limited. So anything that was between those values is some kind of disturbed. So, but again, this is the data that we have. The process of generating the data might be uncertain, and most of all, our knowledge about parameters is uncertain. What is happening in the process, we cannot say what's happening in the process, what's the actual value, because we cannot decompose the process to parts, because everything will be more complicated. However, we can assign the probability of what the values of the parameter are most probable. So for example, we can assign the probability that we'll assign, let's say, 95% probability that the value of parameters will be between -1 and -1.1, right? So we can get this aspect here. So every parameter is uncertain, but the data is what we have. So data are numbers, everything else is uncertain. Second thing, in classical statistics, we use data, period. We get data, we infer about data. We get some kind of structure, but that's it. We cannot add any knowledge about the parameter values of our model that is not represented in our data. In case of Bayesian statistics, of course, we can. We can assign probability distribution to the parameters that we have that represent our prior knowledge. And this is the main problem. First of all, parameter is not a value but a distribution, so we only have an uncertainty, so that's why we can use it. And moreover, we can add some kind of we are adding some kind of, let's say, subjectivity to our process. And this is the main criticism of Bayesian statistics by classical statistics, mathematical statisticians, because Bayesian statistics adds subjectivity. You can represent your prior knowledge about parameters in multiple ways, better or worse, and will give you some kind of result. There is not one way of representing your knowledge. But on the other hand, you can, for example, assign the knowledge that certain parameters just cannot go over certain values, or that you know that they will be in this range because we know this from the previous experiments or from the physics or something like that. So we can bound our areas to certain aspects or represent some kind of relationships between two variables because we know that, for example, when one rises, the other rises, so the correlation is positive. So whatever happens, this correlation is positive. For example, correlation between height and weight of a person is positive. Taller people are heavier, right? It makes, this is a positive correlation. And we know that this happens here. You had a question? Or you just were, no, behind you. You raised hand before. No. Okay, so the aspect, we can assign prior knowledge. So we are adding certain subjectivity, but practice shows that doesn't matter. This, in practical aspects, even adding certain subjectivity, we still can get results which will be impossible other way. And if we have a lot of data, this subjectivity does not matter at all. And if you have a little data, this subjectivity might matter in a very limited aspects that are not practical in any way. So, for example, it can skew our estimates by fractions of percent, which are not really that aspect. And finally, in Bayesian statistics, everything besides data has a probability distribution. So everything, every parameter, every element of the model is a probability distribution. So everything is uncertain, and this probability distribution has to be used. This is a change between the classical statistics, because in classical statistics, you have, for example, estimator, unbiased estimator, minimum variance estimator. You have a function that from the data gives you a number. Bayesian statistics, you give it data, it gives you a probability distribution of that number. That's the main difference. And that result has to be some kind of represented, has to be some kind of summarized, either by samples or by expectation or by something else. So generally, that's the main idea. And it was a very long, very, let's say, bitter conflict between Bayesians and the classical statisticians. What's more interesting, both methods start with the same person, Laplace. Laplace has found results of Bayes and constructed what we can call now modern probability theory. And he formulated all the Bayesian results. However, those results, again, were uncomputable at that time. You were not able to solve more advanced problems because they require from you analysis of a very complicated probability distribution, which is a difficult problem. And so he obtained new asymptotic methods that if you have a lot of data, then you can use those, and that works. And generally, there was a very long let's say, battle between frequentists and Bayesians, where frequentists were winning for a lot of time because their methods were more practically useful because you could compute them. However, this changed again mostly at the beginning of the century, because first of all, in certain aspects there was a real big problem of assigning probability for the events that didn't happen yet. For example, the first important use of Bayesian statistics was insurance. How you assign the probability that certain person will have a car accident even if they didn't have it before. How you can assign set probability of fires, floods, hails, things like that, which you have very limited or no data before. And that's where you could add some kind of prior knowledge. And that was being used in, without, let's say, notifying the scientific world, by practitioners in the insurance office that were using Bayesian methods in order to score the to estimate the amounts that people need to pay for their car or personal insurance. Next step was the development of computers, especially in the lab of Turing in the Second World War, when they were using the results of Polish cryptographers, but mostly they used Bayesian statistics with computation to break more advanced German codes. And you can read about all that in a very nice book called The Theory That Would Not Die, with a very long subtitle. And so this is a popular science book when they cover the history of what was happening before and when Bayesian methods started winning. For example, like finding lost nuclear bombs in the ocean. Generally, when we had computers and Monte Carlo methods, which were developed by the same people who developed the atomic bomb, then we were able to solve the problems. And when we were able to solve the problems, then the advantages of the methods started being more and more and more dominant, and now they are being very much used in very multiple aspects because they have significant advantages. And now generally Bayesian methods are competing not with classical statistics but more with machine learning because of different similar resources but different applications. Where we use Bayesian statistics, the most use of Bayesian statistics and most development over a lot of years was in social sciences, politology, economy. Why? Because first of all, you have problems with data. You don't have much data in many cases. You have, for example, single number for an entire country. Second aspect, data is very noisy. When you say when you give surveys to people, those people might not respond. They might lie. So you have returns of, let's say, a third of surveys that you send, which is a great success, and you get and you can get false answers or incomplete answers or something like that. That's why in social sciences, a lot of people were looking for Bayesian statistics, and they developed a lot of mathematics that was needed for that. For example, Andrew Gell-Mann, who is a physicist by education and develops a lot of significant practical results in Bayesian statistics, works as a head of political science department in the University of Columbia, because they work on statistics to predict elections and things like that. They, for example, did a model that collected data from Xbox users during the election. So remember, Xbox users are very non-representative part of the society, right? Because these are generally a younger gamer, mostly male, right? And they made them solve surveys during playing with partnership with Microsoft. And they were able to get, using the information of all those people, so there's some kind of demographical information about location, about the age, gender, stuff like that, and their answer, they were able to create a hierarchical model that represents different types of population and then feed it actual demographical data. And they got very close results to the results of the probabilistic model that was of the actual election. So you could use very unrepresentative, limited sample and still get good predictions because you've used a lot of knowledge and computation. Of course, medicine and biology are good places for that because of similar reasons. A lot of uncertainty, a lot of changes. We can say with a lot of confidence that there is not a single parameter that is the same in two people, right? But we can assign some kind of probability between them, how it is measured, right? And of course, we have problems with patients dropping out of, or not following the medication or stuff like that. So this changes. Many kinds of experimental sciences, when we again cannot repeat the experiments infinitely, and we want to get some kind of order of what we are doing. Diagnostics, so detection and classification of faults or problems, assigning probabilities to certain aspects, and of course decision support, because if we have probability distributions of our parameters in our model, then we can, for example, use them to simulate the data, or in other ways to create a probability distribution of possible data having our knowledge of parameters. And those can be, for example, used to estimate the arising costs from, let's say, certain treatment, certain usage. And we can get the probability distribution of the cost. And having probability distribution of the cost gives us, okay, what is the expected loss, expected gain, how probable is that we will lose more than 10% of our initial invest, or something like that. So those things can be then used to estimate our losses and give us the decision support in a way that we practically need, so we can get what kind of utility can we get from our model. Okay, so generally, what are the main concepts that we'll be using in our course is we have variables that are observable and variables that are unobservable, right? So we have let's say measurements which are related to unobserved actual phenomena. We are measuring flow, but our measurement of the flow is actually a voltage generated by a flow sensor, right? So it gives us representation of a flow, of actual unobservable, but we have the measurement of the flow again from the sensor, right? You understand that? Okay. We have parameters, we have data, and we have predictions. So our model contains parameters, we have data that is obtainable, and then we can predict something using our data and using our parameters of the distribution, so we can get predictions. Generally, we have some kind of observational units, which can be a single measurement, or it can be a group of measurements, for example, entire time series, or a group of people, or stuff like that. We have the concept of exchangeability, which is a very important one, because from the classical statistical courses, you know the concept of individually independent distribution, right? That every sample is independent from each other. And this is a very strong situation because that is not really happening. But we have the exchangeability is a weaker idea that your data can, for example, if we, for example, switch an order of our data, it won't matter. If we have, for example, coin flips with some basic assumptions that it's random and not related to a thrower, right? We have each coin flip does not matter which order that we collected. We only know that how many flips will happen in that time, how many heads, how many tails. But this is general exchangeability. And there's also conditional exchangeability. Conditional exchangeability says that if we have multiple people flipping coins, some people might flip it differently, right? Because coin flip is an act. We can generally assume that if someone is manually efficient enough, they, for example, could flip a coin in a way that it will stand on the edge, right? We've seen people that are doing stuff like that. So if we condition on each person, then throws within each person might be exchangeable, but between people might not, right? So two people flipping coins might have different weights, but one people should have one. And again, we can add this conditioning to a deeper level. Generally, exchangeability is an assumption that we assume that certain data is exchangeable, and because of that, we can do a lot more computation with it. It's simple. We, of course, have, besides our measurements, we have also some of our outputs, we have some kind of explanatory variables or predictors. Those are the values that we want to use to get some kind of prediction, to get some kind of relationship between data. And we, of course, need to be able to handle that. Important aspect is hierarchical modeling. So, generally, the main idea is that we have multiple groups. And in our situation, for example, we have equipment bought in different factories. So we cannot use the same, let's say, model for the failure time, how they fail, because they are produced in different ways. So they are, for example, similar parts that behave similarly, but still each factory has its own kinks, its own issues when manufacturing that. So actual parameters should come from a similar distribution, have similar uncertainty, but they should, let's say, each factory has their own distribution of parts, of parts features, but those distributions still should be similar to each other because it's the same kind of part. So this is this hierarchy. Of course, paths are similar, so results will be similar, but with some kind of variation between each group. And utility distribution, I mentioned before, the idea how to represent our data into simulate our knowledge about parameters from the data into simulated data, and using simulated data get some kind of decision about what happens with this simulated data. And let's give one formula and one simple example, and we'll finish for today. We'll start with the base rule, because if we are moving off Bayesian statistics, we should start with base rule, which is generally the main idea for all this stuff, because it's because how our data is influencing our knowledge about parameters of the model. It all starts with joint probability, which is very important because joint probability is computationally very efficient for what we want to do. And we just says that joint probability of theta and y is probability of theta times the probability of y conditional on theta. Of course, if y is independent from theta, this is just simple multiplication, probability of theta times probability of y. But generally it's not. That's why we want to model it, right? And of course, with very simple transformations, we can do it the other way. So, probability of theta y is equal to probability of y times probability of theta conditional on y. Yes. Either from one side or the other. So, we can, using very simple transformations, we can transport this situation into that probability of theta conditional y is equal to this kind of fraction. This fraction is probability of theta times probability of y conditional on theta, so this part, divided by probability of y. And probability of y we can get from the total probability. So covering all possible theta, using this formula, probability of y will be the sum of all possible of theta times probability of y conditional on theta. Of course, if theta is continuous parameter, it will be an integral with appropriate probability measure, which we won't, of course, we won't discuss. And this part, this probability of y, has one big part. It is not dependent on theta. It's only dependent on the only fixed thing we have, which is called theta. And this is important because this means that this part, being independent of theta and not being a probability distribution because it's dependent only on y, which does not have probability distribution, is only a proportionality factor. So in most applications, we have that the posterior distribution, that means theta conditional on y, is proportional to the product of prior distribution and the likelihood. The prior distribution is what we knew about our model parameters before the experiment happened, before we collected any data, what we knew about it. If our model is parametric, we gave it from parameters. If it's some kind of hypothesis, what we knew about the hypothesis. And the likelihood is generally how well our model fits the data if certain parameters are given. So this is something that you've used, for example, in optimization. Function that assigns to a vector of parameters the measure of difference between true values and what values we've simulated. When you, for example, were designing a PID controller, right? Using optimization, you were varying the value. You were making an experiment and changing for what is the error aspect. So, for example, sum of all errors. And that's the main idea. We have the product of prior knowledge and how the model fills the data. And this gives us the equation for the probability distribution. But because in order for it to here to be equal, we would need to have a P of y in the denominator, then probability, this probability, this would be equal. In this case, we have only proportionality. But for practical applications, it doesn't matter, because if we want to find a maximum is exactly the same place. Multiplication by constant doesn't change anything. If we want to analytically integrate it, that would be a problem. To find something by integration, for example, to compute the expected values. However, in order to generate samples from the distribution, which we will cover in a few lectures, it will mean that it will not be an issue. Okay. What is, however, important is that Bayesian statistics is not about Bayes' theorem. You can use Bayes' theorem whenever you want. However, when you quantify your uncertainty using probability distributions, then you are doing Bayesian statistics. So Bayesian statistics means about uncertainty and not by using Bayes' theorem. Bayes' theorem you can use in classical statistics or any other way, it's always true. It's a very simple result. As you can see, you can devise it very easily from the probability of the joint probability theorem. So this is very simple, very basic, very true result. The aspect of uncertainty is more important in this case. Okay, let's do an example from the BDA book. This is a fun example from Polish people because they wanted to find how someone make a spelling error in the word random. And there's a let's say that's a random word which is called random. And only after analyzing the data they find out that random is not a random collection of letters, but it's a town in Poland, known from its heroes and other airports and stuff like that, and Navy shipyard, I think, military Navy shipyards in London, I think. Really, it was the decision of previous Ministry of Defense that the naval shipyards will be moved to London, like administrative buildings and stuff like that. We only do military ships, but like. Okay, so generally the idea was to, what is the probability of writing random instead of random? And for simplification we get only three possibilities. We could be random, radon or radom. And using that we can assign those probabilities using the base formula. In case this we have the probability of what is the normal probability that writing such letters we wanted random, which can be taken from Google results of spell checking, which can assign these probabilities. What was that? And again, we can get the so it would be our prior knowledge. What was the prior knowledge of wanting to write random? And the likelihood would be the how probable, what is the value of random considering random. Which can goes from the Google spell check model, which assigns those probabilities like here. So all are on the similar levels, not like completely disparate from each other. So each of those can be assigned those values using the Google spell check model. And the likelihood, again, can be obtained from that. So what is the probability of wanting to write radom when it's random? So radom by itself has a high likelihood because it is the real word. So if someone, what is the probability that someone wanted written radom if they wanted to write radom? So this is the probability, how it fits well. So this represents all possible situations, right? Adding to each other. What is the probability of, if we've written random, what is the probability of how our assumption that we wanted to write random? So probability that we've wanted, if we wanted to write random and we've written random, is 97%, which is a large probability. Probability that we've written random if you wanted to write random is probability that we've written random wanted to write random is 0.0019, so it's less than about 0.2%, and the probability that we've written random if we wanted to write radon is again assigned to this. So those are the radon by itself has lower probability of because of us being unrelated to the number of being put into Google search. So we can compute the posterior distribution by itself, doing those computations that we've listed before, multiplying all those things and summing them out, and we can see that the probability of that we wanted to write radom if we written radom is 67%, having that data. So it is still more probable that we wanted that typing radom, we wanted to type radom. However, there is still 32% probability under this simplifying assumption that we wanted to write random. Because still in English language, when we are writing in English language, it is much more likely that we wanted to write about randomness than about being from random. And again, smart woman from random, yes? Okay, any questions? Is this generally clear idea? Prior probability comes from the frequency of certain words in language, in this case. Likelihood comes from the Google model and recording of data corrections. So how was those correct usually? And posterior is the computation. And this is the most basic example, which can be done on card and does not require you to do HIV tests of terrorists or terrorists. They are those most popular example of Bayes theorem. But this is how we use our prior knowledge from the spell checker, the model of the spell checker, and the probability to get the result we wanted. Okay, if everything is clear, we see each other on the next week.